Hi everyone. So today we're going to discuss Euclid's GCD algorithm. Okay, GCD basically stands for greatest common divisor. So this algorithm is for the GCD problem, which is that given two numbers a and b, where a and b are both positive integers, we want to find their greatest common divisor. Okay, so this problem can be done in kind of a brute force solution, okay, where the first step of that would be finding all the factors of A, right? Then the second step would be finding the factors of B that are also the factors of A, okay? And finally, so in second step, we'll get all the common factors that A and B have, right? After we found all these common factors, all we need to do is return the greatest of these, right? And that would solve our problem. So this step of finding the factors of a number, it can be done using a simple while loop and the modulo operator, okay? uh, and if implemented properly, uh, we can do it in big O of root of the number time. So to find the factors of A, we can do it in big O of root of A, right? Similarly, for the second step where we have to find the factors of B and that are also factors of A, we can do that in big O of root of B time, okay? If we implement it properly. Now the third step can kind of be clubbed with the second step because we can just maintain a variable that keeps track of the greatest uh, factor that we've seen till now, which is common to both A and B, right? And keep updating that variable again and again in step 2 itself. So yeah, so the entire time complexity of the brute force algorithm comes out to be big O of root A plus root B, right? Now this is good. It's not that bad of a time complexity, but Euclid's algorithm can help us do much better than this. Okay, so what is Euclid's algorithm? To understand this, we need to understand two pieces of information. The first one is shown here on the screen, that the greatest common divisor of A and B is equal to the greatest common divisor of B and A mod B. Okay, here A is the greater number between A and B. So if you guys just want to accept this fact for how it's written, you can skip to later in the video, but we're going to try to prove this right now to gain a little better understanding of what Euclid's algorithm actually is and how it works. So let's try to prove this statement now. Okay, so the first thing we can do is write A as Q into B plus R, right? Which basically means that A, like this is basically a divisor's formula that we learned in math, right, in school. So any number can be written as some quotient into the divisor plus a remainder R, right? So if we write A like this, after this, let's say that the GCD of A and B is actually a number G. Okay, so we'll represent the GCD of A and B with G. Now remember this because this will be important for later on, right? So since the GCD of A and B is G, that means B can be written in terms of G, right? B can be written as G into some K1, okay, where K1 is some number such that G into K1 is equal to B. So A is equal to Q into G into K1 plus R, okay. But now we know that G should also be able to divide A, right? Or G should be a factor of A, right? So the first term that we see here, that has a factor of G, right? So that's good. But the second term R, we can't explicitly see a factor of G in it, right? But if G has to be a factor of A, it should be present in both of these terms as factors, right? So that means that R should have G as a factor of it. Okay. This means that we can write R as G into K2. Okay. So A can be written as Q into G into K1 plus G into K2, right? And now if you look at what we've written B and R as, B has been written as G into K1 and R has been written as G into K2, right? So clearly G is a common divisor of both B and R. Okay. So this is great, but we actually wanted to show that G is the greatest common divisor of B and R. Okay. Because R here is nothing but A modulo B, right? And we want to show the statement, the first statement shown on this page, that GCD of A comma B is equal to GCD of B comma A mod B, right? Till now we've shown that the GCD of A comma B, which is G, is a common divisor of B and A mod B, right? But we haven't shown that it's the greatest common divisor. So this greatest part is still remaining. Okay, which means what we want to show now is that this G, which is a common divisor of B and R, is actually the greatest common divisor of B and R. Okay, so how do we go about showing this? We can try to do this using contradiction method. Okay, so we'll try to prove this using contradiction. So the first step in that is that we assume that there is some other number G1, okay, where G1 is also a common factor of B and R, and G1 is greater than G actually. Okay, so that means that G1 would be the greatest, G1 would be a factor of B and R that is greater than G, right? So we're assuming this. After this, we write B as G1 into C1, okay, because G1 is a factor of B, so B can be written like that. Similarly, we write R as G1 into C2, okay. Now, if we write B and R like this, and we know that A is equal to Q into B plus R, then we can write A as Q into G1 C1 plus G1 C2, right? Now, if we take G1 common from both these terms, we can write A like this, right? This means that G1 is actually a factor of A, right? So what have we seen here? We've seen that G1 divides A, and also we know that G1 divides B, right? Because that's what our assumption was, that G1 is a common factor of B and R, which means G1 definitely divides B. So G1 divides A and G1 divides B, right? We also know that G1 is actually greater than G, right? This means that G1 is a common factor of A and B that is greater than G, okay? But G, by definition, was the greatest common factor of A and B, right? This means that this statement that G1 is a common factor of A and B and is greater than G should be impossible, right? Because G was the greatest common factor of A and B. So G1 can't be a common factor of A and B that is greater than G, right? So this is the impossible statement that we encounter. This is the statement that shows us that there is some contradiction, okay? The contradiction obviously is with the statement that we assumed here, that G1 is another common factor of B and R and G1 is greater than G. Okay, this statement, it was our assumption. That means this statement is actually what is impossible. Okay, and because we can't find any other common factor of B and R that is greater than G, this means that G is the greatest common factor of B and R, right? Which means that we proved what we set out to prove. Okay, so that's great. Now we know that G is the greatest common factor of B and R, and R is basically A mod B, right? But G is also the greatest common factor of A and B, right? This is by definition. This means that we've proved what we wanted to prove, that GCD of A comma B is equal to GCD of B comma A mod B. Okay. So this was the first part of Euclid's algorithm that we needed to, this was the first part of Euclid's algorithm. Now let's move on to the second part of Euclid's algorithm. This is a little simpler to understand. The second part says that we know that we can write A as Q into B plus R, right? If R is 0 in this situation, then we know that the GCD of A comma B is B. Okay, how do we know this? Firstly, we know that B is definitely a common factor of A and B. Okay, because if R is 0, then A can be written as Q into B, right? Which means that B is a factor of A. And B obviously is a factor of itself. So B is a common factor of A and B, right? But how do we know whether it's the greatest or not? This is because the number B cannot have a factor that is greater than itself, right? All factors of a number are either lesser than or equal to it, right? So if I want to find the greatest common factor between A and B, that can't be greater than B, right? So that means that in this situation, B is actually the greatest possible common factor. Okay, so that's why GCD of A comma B is equal to B if R is 0. Okay, so these are the two things that we need, and both of these together are what are the foundation of Euclid's algorithm. Okay, now understanding Euclid's algorithm will be much simpler. So finally, what is Euclid's algorithm? The algorithm is really simple. All it asks you to do is that given two numbers A and B, you keep using this first equation given here and reducing your problem. Okay, so instead of finding the GCD of A and B, you'll actually find the GCD of B and A mod B. Okay, and then to find the GCD of B and A mod B, you use this same equation again and reduce the problem further. Okay, and so on and so on. You keep doing this until you reach a situation of the second point given here, the second point that we discussed, which is basically that A mod B is 0 or R is 0, right? And in such a situation, the GCD is just B. Okay, so this is kind of a recursive solution. That is what it actually is. So you should think of that in this in recursive terms. Okay, let's see this again like a little more properly. So what it's basically saying is that suppose R is A mod B. Okay, then Euclid's algorithm wants you to find GCD of A comma B by actually calculating GCD of B comma A mod B or B comma R. Okay, now how do you get this GCD of B comma R? You again use the first equation given here. Okay, but now on the LHS, the two inputs are B and R. Okay, which means that to calculate GCD of B comma R, you should now try to find GCD of R comma B mod R. Okay, using this first equation on the page. And then to further find GCD of R comma B mod R, you again use this first equation. Okay, and so on and so on, right? You keep doing this until you reach two numbers, say C and D, where C mod D is actually 0. Okay, or the remainder when you divide C with D is actually 0. Okay, in this situation, the second point comes into play. Okay, so according to the second point, GCD of C comma D in such a situation will actually be D, right? So your final answer will actually be D. Okay, so to make this a little more elegant, what we actually do is we stop the algorithm when our second number becomes 0. Okay, instead of stopping it here, what we'll do is when when we are asked to find GCD of C comma D, we'll just again use the first uh, equation here blindly. Okay, and because we're using the first equation here blindly, so what we'll be asked to find then is GCD of D comma C mod D, right? But C mod D is actually 0. Okay, so we'll be asked to find GCD of D comma 0. Okay, and when we see that our second number is 0, then we should stop the algorithm and the answer will just be our first number, D. Okay, because in the previous step, seeing that the second number we are getting here is 0 would mean that in our previous step, C was actually divisible by D itself. So the answer is D, based on the second point given, right? So that's all that the algorithm is. Okay, that's how you can keep breaking the big problem you have into a smaller problem and smaller problem recursively until you reach this base case of the second point given here. Okay, or the base case that your second number uh, is actually 0. Okay, so that's it. That's Euclid's algorithm, and the time complexity of this is big O of log of b. Okay, so this the exact calculation for this time complexity is a bit mathematically involved and not really that important from a computer science or computer programming perspective. So we're going to skip that, but it's really important to note that this is the time complexity that we get if we use Euclid's algorithm. It's big O of log b. Okay, what this means is that this is a significant improvement over big O of under root a plus under root b, right? We are now able to solve the problem in a logarithmic time rather than a polynomial time, which is why Euclid's algorithm is a great algorithm to calculate GCDs. So now that we've discussed the algorithm and the time complexity, we should probably go and try to implement it practically. So let's do that. So we're here on Geeks for Geeks, and the questions here. So let's try to implement it. So what we want to do is that first we can make like our helper function, okay, which is basically the recursive function that will calculate the answer and give it to us. So let's call that Euclid GCD, right? And the numbers that will be passed to it are the greater number a and the smaller number b. Okay, now the base case as we discussed is that if b is 0, then we should return a, right? But if b isn't 0, then the answer is actually GCD of b comma a mod b, right? Using the formula or the recurrence relation that we had, and then we can just return this answer. Okay, so that's all for our helper function. Now in the main part, what we should do first is actually find out which one of our inputs is bigger. Okay, so the inputs here is capital A and capital B. So let's say that x is equal to max of capital A comma capital B, and y is equal to min of capital A comma capital B. Okay, now that we found this, we can just return the answer that we get from our helper function, right? X, this we give the larger number first and the smaller number after that. So that's it. That's all for the program. This should work. Let's try to compile it first to see if there are some typing errors. So it does look like it. Does look like there are some compiling errors. Yeah, so here is the error that we had. Instead of GCD, we had to write Euclid GCD in the recursive function also, right? Yeah, so we just wrote GCD instead of Euclid GCD, which was our recursive function's name. Now this should work. Great. So it does work. Let's submit it to see if it passes all the test cases. Yeah, it does pass all the test cases and we solve it correctly. So that's great. This was the recursive implementation of the Euclid's algorithm. But in case you aren't familiar with recursion yet, or you have some harsh time or space constraints that don't allow you to use recursion, we can also use a iterative version of Euclid's algorithm. Okay, so that won't be too different than what we've done here. So to convert this into an iterative implementation, what we can do is observe that we're just making one recursive call, right? In our function, we're just making one recursive call, and that too is a tail recursion. Like as soon as we make this recursive call, all we're doing is returning the answer, right? We're not doing any other operations. So this means we can easily convert our recursive function into an iterative approach by just simulating the change in values, okay? Or by simulating these function calls by changing the values of the variables, because that's what's essentially happening. So if we look at the function here, the values, input values given to it were a, which is the larger number, and b, which is the smaller number, right? So as long as this smaller number isn't 0, what the function does is it changes the value of the larger number to the smaller number. Okay, it changes the value of the, or in other words, it makes the new value of the larger number equal to the value of the current smaller number, right? And the new value of the smaller number equal to this remainder a mod b. Okay, so if we can simulate this in a loop, then that's all, we'll be done. So let's try to do that. I'll just change these variable names to a and b so that it's easier to follow. And now we don't need this statement here. So what we're going to do is, while our smaller number b is not equal to 0, okay, so throughout this loop, what is going to happen is a is going to remain as my larger number and b is going to remain as my smaller number, okay? And each iteration of this loop will just update these values of a and b to the next iteration or the next call, that to the next values that they were supposed to have based on our recurrence relation, right? So while b is not equal to 0, what we should do is first find the remainder, which is a mod b, okay? And now the new value of a, which always should be my larger number, okay? The new value of the larger number is the current smaller number, right? So that means a is equal to b, and the new value of the smaller number is equal to r, right? And this loop will just simulate our recursive function there, and when this loop ends would be when b becomes 0, right? So whenever this loop ends, all we have to do is return the larger number a, okay? And that's how we implemented our Euclid's algorithm using an iterative approach. So let's try to compile and run this once. Yeah, so it does work. Let's try to submit it now. Great. So that's all for this video. We discussed what the Euclid's algorithm is, and we implemented it in a recursive implementation as well as in an iterative implementation. I hope everything was clear. If you guys have any doubts, please feel free to leave them in the comments, and thank you for watching.